I will be talking about infinite groups. So hello, lovely to see so many familiar faces. Yeah, we'll be talking about infinite groups. I should first of all say everything today is kind of inspired by and partly taken from a course I took a few years ago, given at Cambridge by Dr. Henry Bradford. So credits go to him. Yeah, if you have any questions, please feel free to interrupt. Questions mean, one, I've got something wrong, which is my fault, or two, I haven't explained something well, which is even more my fault. So if you don't understand something, throw something at me, make it clear. Okay, let's set the scene. It's a rainy day, 18-year-old Segev in his room, crying over groups. I had much shorter hair, probably stupider glasses, made the same terrible jokes. And as I'm crying, I start crying even more, and I think, where are all the infinite groups? In my groups course, we did dihedral groups and symmetric groups and simple groups and blah, 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 blah. We did some infinite groups. We saw the integers, maybe the reals, not very interesting. Maybe some linear groups, right? SL3Z, SO3 maybe. Where are the infinite groups? The short answer is infinite groups are really hard. Really, really hard. Just as a representative example, in a general abstract infinite group, we can't even tell if a given element is the identity. I can give you a group, and I can give you an element, and you won't be able to tell me if it's the trivial element. I'm assuming everyone here knows what groups are. Is that a safe assumption? Cool. This is sort of the starting point of a blossoming field, if I may say, called geometric group theory, which aims to study groups. How does it do that? The best way, or one of the best ways to study a group is to look at the things it acts on, and that's where the geometry comes in. We find a group, we find things they act on. In many cases, there isn't really a nice thing the group acts on, apart from itself, and then we study the geometry of the group itself. As I say, geometric group theory is sort of a blossoming field, really came into its own in the 80s and 90s, but it can be traced back to the work of Hamilton in the 1850s on icosahedral symmetries and all that kind of stuff. And yeah, it has links to low-dimensional topologies and operator theory and loads of stuff. But let's return to the basic question that I tried to pose today. I have an infinite group. I don't know how to understand it. So let's try and understand it using finite groups. Now, even this question isn't particularly well defined because there are loads of different ways of interpreting that. Geometric group theory is a field rife with examples and counterexamples and paradoxes. I've just written here a representative sample of some suitable definitions of what it might mean for a group to be approximated by finite groups. We're not going to be looking at all of these. Upwards arrows indicate inclusion, strict inclusion. All of these are very strict. Today we'll be looking at sophic groups, well, finite groups, and if time permits, we'll be looking at amenable groups. So there's a whole universe of groups left to discover. And again, this is a tiny sample of the different kinds of groups we can find in our universe of groups. I was going to say something else. Anyone remember? No? Okay. Cool. Let's start with finite groups. What does it mean for a group to be finite? Not a trick question, Lucas? Oh, what a terrible answer. Yeah, so that's a good answer. A group is finite if it is finite. In particular, that means we can count things. And as I say, time permitting, we'll come back to that idea with amenable groups. But let me try and convince you why that's a terrible answer. Sorry, Lucas, but it was. Let's look at these two groups, the cyclic group of order 60. Oh, yeah, if someone can't see anything I write, please let me know. Cyclic group of order 60. And the alternating group with 5 elements. These two have the same cardinality, but they're very different as groups. Their behavior is vastly different. So cardinality does tell us they're finite, but it doesn't tell us a lot about the group themselves. Even worse, we'll be talking mostly about finitely generated groups today, which are groups that have a finite set of elements that generate all the other elements. they're all countable. A finally generated group has to be countable. And so defining a group as approximated by finite groups through cardinality alone doesn't really tell us much, because finally generated groups, basically everything can go wrong, and yet they're all countable. So yeah, let's get rid of that. I think that's the only time I tried to trip up anyone in the audience, so sorry it fell to you, Lucas, but I was kind of hoping it would fall to you. So, okay, let's look at a different sort of, is there a rag somewhere? Whatever. Let's try and look at a different, more intrinsic definition of finite groups. What do we know about finite groups? Each element of the group permutes all the other group elements. Right? We get an element, we have a list of all the other elements, and we see what happens when we multiply each of the other elements by this group element. In particular, this is a theorem called Cayley's theorem, which is one of those theorems that feels even stupid to even state at times, but a group, oh my God, my handwriting, can you see, is that too big? Is that too small? Cool. Is finite if, I'm going to leave some space, you'll see why in a second, there exists a phi from gamma to some symmetric group, right, this is just some symmetric group, such that, firstly, phi is a homomorphism, and secondly, phi is injective. I'm writing it in a really stupid way because you'll see why in a second. But all I'm saying is a group is finite if and only if it's a subgroup of some symmetric group. That's easy. That's Cayley's theorem. Again, the proof is, well, a finite group acts on its own set, on its own elements by permutations. Okay. Before we advance, I want to introduce a way of measuring how things are different in here, otherwise known as a metric. It's called the normalized Hamming metric. I'm not going to write that down, but it's the normalized Hamming metric, and it just measures how far permutations are by seeing how many objects they move to different things. So two permutations are close if they do almost the same thing to basically everything, right? This is a suitable metric. I want to rephrase being a homomorphism in terms of this metric. Phi is a homomorphism just means for all, let's use x and y, the distance of phi xy to phi x times phi y is 0. Right, that just means that phi xy is phi x, phi y. That's what a homomorphism means. And I want to rephrase injectivity in terms of the distance, the metric. So for all x and gamma, the distance from phi x to the identity is 1. For all x non-trivial. It's even better than just injective. It means every element other than the identity has no fixed points in this representation. And that's easy, right? If we take n to be the size of the group, every element has no fixed points other than the identity. Okay, this lets us generalize what we mean by finite group in a very nice way. First of all, we're going to need to come up with a name. Can't possibly be using finite still. Let's pick a different language. Let's just speak Hebrew, because why not? The Hebrew word for finite is sophi. Sounds a bit weird. Let's add a C at the end. Let's call these groups sophic. And this is now definition. A group gamma is sophic if, this is why I left space, for all finite subsets and for all epsilon greater than 0, there exists a phi from A, where's my other chalk, into a symmetric group, such that we can't possibly ask for it to be in homomorphism, right? Because otherwise our group is probably going to be finite itself or very close to it. So let's ask for this to be less than or epsilon. It's almost a homomorphism. And it almost has no fixed points. This is going to be greater than epsilon. Greater than 1 minus epsilon, sorry. Okay. Yeah, replace here with A. We only do this for finite subsets. Why? Because it's the only thing we can really get a grasp on. These were introduced by Gromov in 1999 to solve a problem in topological dynamics. Well, not to solve. He proved that a certain property holds for Sofic groups. We'll be doing something different with another property that might hold for groups. That's kind of the aim. In the meantime, let's see a few examples. Finite groups are clearly Sofic. I hope that's clear, right? Any subset in particular is a subset of the group, and we have these homomorphisms into finite groups. That's Cayley's theorem, into permutation groups. Z is clearly Sofic. Take any A, subset of Z finite. Maybe I'll write finite. In particular, A is a subset of some interval. And then we can consider phi that sends, well, take, I don't know, m greater than or equal to m plus 1 should suffice. Take phi that sends, well, okay, consider, whatever. Take an n cycle in sim m. So consider one, let's call this sigma, 1 to up to n, an n cycle, and then send an a in here to sigma a. You can check that this satisfies these conditions with epsilon equals 0. You don't even need epsilon greater than 0. This satisfies for epsilon equals 0. In particular, Z is Sofic. So far, so good. Subgroups of Sofic groups are Sofic. Right? Why? This is kind of a local property. It only depends on finite sets in our big infinite group. Any finite set of a subgroup is a finite set of the whole thing. So clearly that holds. Gamma is Sofic if and only if all its, I don't know why I did, for all finitely generated subgroups are. Again, it's because this is a local property. Take a finitely generated subgroup, take any finite set. In particular, it's a finite set in the finite, sorry, a finite subset of a finitely generated subgroup is a finite set of the whole thing. Conversely, take any finite set in the whole thing, see the subgroup it generates, that's finally generated. By our assumption this way, it's Sofic, so this is Sofic. Again, Sofic is a local property. Let's do a few other examples. If two groups are Sofic, then their product is Sofic, their direct product. You might ask whether this holds if I change it with a semi-direct product. We don't know. We suspect the answer is no, but we don't know.
What is a semi-direct product?
Good. Let's ignore that. It's a generalized type of product. Another way of thinking about it is if... okay. I'll say the word extension like 2 times. I don't want to give a formal definition, but let's just say gamma is an extension, and you can prove that extensions and semi-direct products are the same thing of n and a if n is normal in gamma and gamma mod n is isomorphic to a. So saying gamma is an extension of 2 groups just means it's kind of built out of these 2 groups, and the way it's built out is what is known as a semi-direct product. Those of you that have done some homological algebra, you'll recognize this as just a short exact sequence, but I'm not going to say more about that. Cool. How do we prove this? Well, we just consider a map from sim x cross sim y to sim x cross y. There's an obvious map that does this, right? Just take a permutation here, take an element here and here, and just apply the permutation from here on the element here, permutation here from the element here. You need to show that it behaves nicely with this Hamming metric, and then you get sophicity from the sophicity of these 2. I don't know if sophicity is a word people say, but whatever. Okay, these are all the examples I wanted to give.
Did you say that when the group is finitely generated, it is Sofic?
No. This is a good thing to the point I was going to say next. We don't know of any non-Sofic groups. It's a conjecture that all groups are Sofic. I think the general consensus is that we don't believe this conjecture is true. There's a general quote in maths, in group theory, I think it's due to Gromov, but correct me if I'm wrong, that says everything in group theory is either trivial or not true. proving that every group is sophic is definitely not trivial, so it's probably not true. This is what geometric group theory comes from. All these counterexamples, everything kind of isn't true, or is true but very hard to prove. I mean, trivial to prove, of course, if it's true. Okay, yeah, so we don't know if there's any non-sophic groups, but we can say perhaps a counterintuitive point. Theorem, we're definitely not going to prove this. If there is a non-sophic group, then there is a finally presented one. I've told you what finally generated groups are. Finally presented groups are even better. Whatever. If you know what finally presented is, good. That's perhaps surprising. In particular, finally presented is finally generated. If you don't know what finally presented is, no, this is a very surprising theorem. That's all I'm going to say. Okay, let's see what we can do with sophic groups. Maybe I'll move this up. Is that what I wanted to say? Yeah. As I say, we don't know. And it's a very hard problem. It's at least as strong as the Kern's embedding problem, if you've heard about that, for group algebras, for group C-star algebras. I'm definitely not going to talk about that, but it's a very, very strong conjecture. That probably isn't true. Okay. When I drink water, can you hear me like gulp really loudly? Or is that just me? No? Okay. Okay. Say we have a countable sophic group. Countable in particular means we can take an increasing union of finite subsets that cover the group. Right? Each of these, by our sophicity assumption, each of these has a representation satisfying the above with 1 over n. So let's take phi n and an 1 over n representation into whatever, some function of n, let's call it psi of n. Right, an 1 over n representation just means something satisfying the above with the subgroup an, with a subset an, and with epsilon equals 1 over n. It's important that we take subsets and not subgroups in the above definition, because all finite subgroups clearly have this property. So if we say finite subgroups in the above definition, it's empty. It's meaningless. Okay, in particular, what can we do? We can try and define a map from phi, from our countable sophic group into the product over n of these symmetric guys. Let's just call this group, to save myself effort, just fancy G tilde subscript phi, just so we remember. The problem with this map is, well, eventually every element is in one of these ANs. So eventually, for high enough n, this map is defined. But it's not really defined for small n. We kind of want to make this map work. So we're going to be studying this little guy first. We can define something known as a pseudometric, which I'll just give as a map on here to the positive reals that just sends a sequence of permutations. Right, what is an element of here? It's just a sequence of permutations in these symmetric things. And it sends it to the limit of the Hamming distances. Sorry, this is a sequence. It sends a sequence to the limit of the Hamming distances. Everyone happy with that? Are you sure? Why does the limit exist? It doesn't. This is where I'm going to have to lie to you. We're going to take a fancy limit called an ultralimit. We're doing non-standard analysis. We're requiring the axiom of choice for this to make sense. It's, I think, technically slightly weaker than the axiom of choice, but whatever. I don't want to talk about ultralimits. We can talk about them after if you're interested. Whatever. Non-standard analysis, this limit definitely exists. This gives us a pseudometric. Why is it only a pseudometric? Because things can have zero distance and not be the same. So let's define n is just the subgroup of these sequences such that the distance above is 0. This is a normal subgroup, you can prove that. And then we get a nice group with a nice metric, which I'll just call G, quotient of this G tilde by n. Whatever. All that matters is we have a group that has a very nice metric, and from the definition of sophicity, what am I trying to do? Okay. From the definition of sophicity, we see that we have an injection from any sophic group into one of these guys, one of these things. This is just what I'm saying here. We just send each element to its representative in the quotient. The representative, well, another fact about ultralimits, a non-principal ultralimit, if anyone cares about that, they don't care about finite things. So any element that we send an element to what happens when it's eventually in one of the ANs, and anything before we can do whatever, because finite things are ignored. Anyway, we have an injection, and this is a characterization of Sofic. Exists this injection if and only if gamma is Sofic. I've sketched the proof of this direction. We're not going to do the other direction. But it's kind of similar. It's just playing with the definitions, and it's slightly more involved. OK, why do we care about that? Let me introduce another object called the group algebra. Have people seen group algebras? Actually, I know you've, yeah, you know, that would have been. OK, let's take a field K, and we'll define the group algebra to just be finite sums. Well, let's just, instead of trying to be formal, let's just say what it looks like. Things of the form, which notation do I want? AGG, such that AG is in K, G is in gamma, and sum is finite. It's just we take our elements in gamma, we just add them, we multiply by some things in K, we get a vector space. If gamma is finite, it's a finite dimensional vector space. Ah, welcome. And we can multiply two elements in the group, right? We want G times H to be GH as a generator of this as a vector space, if you see what I'm saying. And we can just extend this to get a ring. This thing is a K algebra. In particular, it's a ring. Again, I can do this in more detail later if you want, but there's not much point. For a general ring, we can ask a question, and I'll give it as a definition. A ring is directly finite, and I'll just write df if AB equals 1 implies BA equals 1. For all elements, if AB is the identity, then BA is also the identity. For commutative rings, if this ring commutes, well, there's a unital ring. We do have a unit. For commutative rings, they're clearly directly finite. If gamma is if gamma is finite, this thing is a finite vector space. And by rank nullity, you can show that this also holds. The question is, are all group rings directly finite? Maybe I should erase the top, because we're not going to need the definition of Sofic anymore. We're now going to use this definition of Sofic. It's so much easier when you just move them by hand. I hate the... Oh, I need more water. Yeah. Anyway, so Kaplansky, fancy name, in 1969 proved that all group rings are directly finite. These group algebras are directly finite if the field K is characteristic 0. In particular, if it's the complex numbers, then they're directly finite. And the general conjecture is that they're always directly finite. I should say as well, while I'm rubbing out, Kaplansky had like 3 other very important conjectures about the K gamma. One of them was disproved 2 years ago, 2021, by Giles Gardner. Very interesting. He found a very cool counterexample. Not to this one, to another one. Why is this relevant for us? Theorem, Alex Szabo in 2004. So very recent work. gamma, if gamma is sophic, then K gamma is directly finite. So if all groups are indeed sophic, then Kaplansky's direct finiteness conjecture holds. We don't know that, but it would be cool. What time is it? So I was going to sketch a proof of this, but I'm thinking I'm quite slow on time. 12:40. Maybe let's sketch a proof quickly. I say sketch because I'm going to not do all the hard bits. How do we start? Given a symmetric group on n generators, I can embed it in the set of the group of endomorphisms of n-dimensional K-space. How do we do that? By sending a permutation here to a permutation matrix here, right? Just a matrix that permutes the basis vectors, like this element permutes the things. We can define a metric on this guy by just defining, let's call this map P. Defining the distance of two, matrices to be their rank, the rank of their difference, normalized. Why is this the right metric to define? Because you can check, exercise if you want, that the metric on this that we defined earlier, the Hamming metric, which is no longer on the board, and the metric here coincide, as in P of sigma, P of tau, is the same as whatever. So this is the right metric to take if we want to keep our Hamming metric here. And that's why I haven't decorated them with anything else, just dn. Okay, now we can extend this map linearly from P to the group algebra over the symmetric of n. And by doing the same construction we did for fancy G over there, we can similarly get a fancy R. Fancy R, which is just exactly the same construction there, but with group algebras, there's no point doing it. I'm forgetting something. Oh, no. Okay, we have this thing. Oh, I said fancy G. By sophicity, our normal group algebra injects into here. And now, by doing the similar construction with these guys, we can get fancy R, psi, with the same function on the naturals, whatever. If we can show that this is directly finite, we're done. Because this injects into this, which injects into that. Okay, it doesn't actually inject into that. Shh, don't tell anyone. If we can show that this guy is directly finite, then we're done. How do we define this guy? Exactly the same construction as above, but with this metric. Say a Bn in this guy satisfy. Just to be more explicit, it's a quotient of just the sequences of these things, the product of these things over the things that have zero distance from the identity, something up there. Let's call it M psi. Say an plus a and bn in R psi satisfy that, let's call this A, let's call this B, that AB is the identity plus M psi, as in the identity in this ring that we're interested in. That means that the limit as we take the limit, again, over the ultrafilter, I'm not telling you what this limit is, that's on purpose, of the distances is 0. And how did we define this distance? I keep on moving the boards too much. This is the rank, 1 over n, the rank of a and bn minus the identity matrix, which you can just show is the same as the rank of bn an minus the identity matrix. And so the fact that this goes to 0, and well, the limit of this guy is the distance of bn an and the identity, And so if this goes to 0, just by doing finite dimensional vector space stuff, this must go to 0. I know I haven't explained anything and you guys are probably confused. And I've lied because this is not an injection, so we can't quite use that. Whatever, talk to me after if you do want to hear more details. But this is another reason that Sophic groups are cool. If all groups are Sophic, then this big open conjecture from 1969 is solved. Okay, is this a good time to move on? Ah, perfect, cool. I earlier bullied Lucas a bit for suggesting a terrible definition of what it means for a group to be finite. I'm now going to take that back and say that was an excellent answer. What can we do on finite groups? They have a cardinality, we can count. Let me be more precise. It's just so much easier to pull it up. We have, let's say gamma is finite. Oh yeah, end of Sophic topic. Sophic topic, that rhymes. Now we're going to move on to amenable things. We have 15 minutes. I'm just going to rant about them for a little bit. Oh my God. Gamma is finite means let's take a finite, well, any subset, and define this object is just the size of our set over the size of the group. We're just counting elements in any subset. We can do that because we have finite things. What is interesting about this map? Well, it has 3 nice properties. The first is, let's just call it PM, probability measure, in that mu of the group is just 1, right? Counting all the elements is counting all the elements. I know it's, whatever. It's finally additive. Yeah, it's finally additive, which means mu A plus mu B is mu A union B if A and B are disjoint. For the probabilists at the back, it's a finitely additive probability measure, not a sigma additive probability measure, I know. And the third thing is it's left invariant, which means mu of GA is mu of A. Right, if we translate all the elements here by G, we don't change the number of elements. We still have the number of elements. This is called a, well, left invariant finally additive probability measure. 1 second. We'll call it a LIFAPM. Yes? G is an element in the group. For any element in the group, if we translate all the elements to the left, we still have the same elements. Cool. We call it a LIFAPM, left invariant finally additive probability measure. And definition, a general group, gamma is amenable if it admits a LIFAPM. Amenable groups are great. They've been around since the 30s, I think. Since von Neumann, I think, was the first person to introduce them. They have like 20 equivalent definitions. If you go on the Wikipedia page, there's a long list of equivalent definitions for amenable groups. This is just one of them. The annoying thing about the definitions for amenable groups is a lot of the equivalences are non-constructive. I was talking about this with Philemon earlier. So even though the definitions are equivalent, if I give you another definition, for you to actually give me a left invariant finally additive probability measure, doesn't really work. An example, Z. Z is amenable. I can't constructively give you a left invariant finally additive probability measure. I know it's amenable from other things called Thollner sets, but the construction of this thing is, I can't actually give you one. So, warning, I guess. Oh yeah, and these amenable groups satisfy much stronger closure properties than the Sophic groups. So amenable, first of all, implies Sophic. We're also not going to prove that, but amenable groups are Sophic, as you can see from my handy picture up there. This is best proved using another definition of amenability that, again, we're not going to discuss. But proposition, amenable groups are closed under, well, subgroups and quotients, as were Sophic groups. Extension, which was the thing I was talking about before. Sophic groups, again, as far as we're aware, are not closed under extension, or we don't know. And these things called direct limits. If you've done some homological algebra, you might know what that is. If you don't worry, ignore it. Let's just prove one of these. Why not? Let's prove quotients. If we have a left invariant probability measure on gamma, and we have n subgroup of gamma, then we have a projection map from gamma to gamma mod n, and we can define a measure on the quotient to just be what is known as the push forward of this measure. You can check that this works. What do I mean by push forward? I mean, take any subset of this, see what its preimage is under this map in here, and just associate that measure. Right? So subsets here in gamma have a measure, have a size. I take a subset here, I pull it back, I see where it came from here, and just give it that measure. This is what I'm saying here, and you can check that this indeed gives a well-defined left invariant finally additive probability measure on my quotient group. So this, amenable groups are closed under quotients. How much time do I have? Okay. Yeah. Oh, sorry, I thought you said something. What did I want to do? Yeah, as I said, amenable groups are sophic. We're not going to prove that. You might ask if there are non-amenable groups. We don't know if any non-sophic groups. You might ask if there are non-amenable groups. The answer is yes, and we're going to prove it. Does everyone know what the free group on two generators is? No worries if not, we'll talk about it. You don't? Okay, cool. I can get rid of this. Okay. I'm just going to say, so we'll show that this nice group called the free group on two generators is not amenable. That is related to the Banach-Tarski paradox that unfortunately I don't think we're going to have enough time to prove, which I did anticipate, to be fair. But yeah, I mean, the Banach-Tarski paradox that you guys have all heard about, as in you can decompose two spheres in this weird way, and you can decompose one sphere into two, and they're the same even though you haven't changed anything. You probably saw a Vsauce video about it once. Essentially, it relates to the non-amenability of this special group, of this free group and two generators. Why? Because amenability, by the definition, kind of means that there isn't a reasonable way to count things. Or there isn't a reasonable way to count things that remains the same when you translate things. And once you have non-amenability of this group, you just let it play with the sphere, and you use the fact that there's no reasonable way to count things in this group to show that there isn't a reasonable way to count things in the sphere. That's the idea. Again, if you're interested, we can give more details later. What time is that? Oh, dear. Okay, yeah. So this will be the last thing I prove. Proposition F2 is not amenable. F2 is sophic, though. We won't prove that, but you can prove it. Let me just say, any subgroup of any amenable group, any subgroup of an amenable group is amenable. So this means that any group that contains F2 isn't amenable. This was a long-standing conjecture of von Neumann from 1929, and Day from 1956, if I remember correctly. I have it written down. 57, got it off by 1 year. That, yeah, gamma is non-amenable if and only if it contains a copy of this thing. This is true for linear groups. So, who proved this? Okay, this is called the Tits alternative, named after Jacques Tits. Tits alternative. This is a slightly weaker version of it, but whatever. If gamma is linear, as in is a subgroup of some GL nk, then the von Neumann Day conjecture holds. But in general, it's false. This was proved by Olshansky in the 80s. the von Neumann-Day conjecture false in general. He constructed these groups. We call them Tarski monsters. As I say, geometric group theory has loads of these weird and wonderful examples. Okay. There's another conjecture I wanted to state, but I should just prove that this guy is non-amenable. Okay, yeah. Let me first of all define what the free group on two generators is. There's a lot of equivalent ways to define it. Which way do I want to do? Yeah, okay. Let's take two symbols, A and B. Let's introduce their inverses, A inverse, B inverse. They just operate exactly as you would want inverses to operate, right? We multiply this guy by this guy, we get the identity. Multiply this by this, we get the identity. Here we have a set of elements. Let's just consider words in them, just lists of things in these four elements, where every time we see B, B inverse, we get rid of it. Every time we see A inverse, we get rid of it. Every time we see B inverse B, we get rid of it. Every time we say A inverse A, we get rid of it. That gives a group. That's the free group on two generators. Very important group. It gives a group. You can check that. Let me draw this group maybe. Let's say we have the identity. This is where I want two colors maybe. Where can I go from the identity? Well, I can either have an A. Let's just draw that as going up. Or I can have an A inverse. Or I can have a B. Why am I trying to do it with my left hand? Or I can have a B inverse. Okay, once I've gone to A, I can either have another A, or I can have a B, or I can have a B inverse. I can't really have an A inverse because I'll just come back to the identity, so whatever. Similarly, at B, I can either do A inverse, or another B. At B inverse, I can do A inverse, or another B inverse. And at A inverse, I can do A inverse, or B inverse. I'm going to switch colors because it's too... And we just do this at every point. At every point, we can branch out, and we get all these little branches. It's just a ternary rooted tree, if you know what that is. Universal cover of this shape, if that means anything to you. Fundamental group of this shape. Whatever. Why is this group not amenable? In short, let's take this, and let's take just this. If I act on this by A, I get all of this. Well, if I act on this by A, well, I have to go back here, and all of these things go here, and this thing goes here, and I get all of this. Similarly, if I act on this thing by A inverse, I get all of the rest. And this is exactly the idea. There's no suitable way. I can prove it. I can actually write it down, but there's no point. This is the intuition, because I've got 1 minute left. Yeah, this is the intuition. I act on A means going up. These two go here. This goes here. And all the little branches I have everywhere just expand. And so, in a way, obviously, there's no way to reasonably count this set, because counting this set will be the same as counting all of these, and this is a strict subset of that, and this is called a paradoxical decomposition. And again, this lack of being able to count this set is exactly the Hausdorff Banach-Tarski paradox. That's where it comes in. Should I say one more thing, just because it's cool? Yeah, completely unrelated. Above, I gave 4 ways of getting amenable groups, and I told you that Z and finite groups are amenable. Good question. Are these all the amenable groups? As in, I take all these operations, take Z and finite groups, and see what groups I can build out of them. This was a long-standing open problem. If we call groups that we can obtain through these repeated processes elementary amenable, I'll just write it EA. And the question was if all amenable groups are elementary amenable. And the answer is also no. And this was done by Grigorchuk and Chu in the 80s. So even this, I guess it was expected to hold. Also, that isn't true. You can construct this weird group that acts on the tree that is amenable but isn't elementary amenable, isn't obtained from repeated application of these things. Okay. I think that's a good point to end. So, yeah. Any questions?
The definition of the Sofic groups basically plots the distance between these phi of xy and phi x, phi y. Can we say something about the local homological properties of its Cayley group, Cayley graph, or some characterization of it? Because I mean, the definition is kind of pointing towards that direction.
Again, all of these things, geometric group theory is, in a sense, the study of how the Cayley graph relates to the geometry of the Cayley graph. So the answer is yes, you can definitely rephrase it in terms of like finite sets of the Cayley graph and whatever. But I don't think it's any more illuminating than that. Some of you, those probabilists would have probably seen, amenability in terms of graphs. And again, amenability of the graph, amenability of the Cayley graph of a group is the same as amenability of the group. These things, groups and Cayley graphs, in a sense, are kind of the same up to this geometric construction. But yeah, so the answer is yes, you can definitely rephrase it in terms of Sofic groups, in terms of Cayley graphs, yeah.
Another question, can we obtain every Sofic group as a direct limit of amenable group?
Yes, so amenable groups are Sofic. A direct limit of amenable groups is amenable, so it's Sofic.
No, I'm asking if every Sofic group can be obtained as a direct limit of amenable group.
No, because all direct limits of amenable groups are amenable. There are non-Sofic, well, F2 is Sofic and non-amenable. So it can't be obtained. Yeah, as I say, there's loads of these examples of groups that are Sofic and not amenable and other properties that we don't know if a non-Sofic group. Let me maybe say another big theorem, Alex Szabo, I think in 2003, around the same time as they did the Kaplansky thing. They proved that if gamma, oh my God, am I going to get this right? Gamma mod n Sofic and n amenable, these imply that gamma is Sofic. I think I might have got these to the wrong way around. But an extension of an amenable by a Sofic group, a Sofic by an amenable group is Sofic. That's quite good. But much more than that we can't do. We don't even know if this guy's Sofic and this guy's finite, if the extension is Sofic. We don't know that. We might be able to prove it one day, but we don't know. Okay.
One thing about this lit tab for Z, so you said it was non-constructive, but I don't even see like intuition for it to exist because it's like a translation is very
Okay. Other definition of sophicity is that we have these things called Foner sets. Sorry, not sophicity, amenability. That we have these things called Foner sets, which are subsets of our group, such that they go to the whole group. And for all G in gamma, does everyone know what a symmetric difference is? I know you two do, because we talked about them. But the rest... another definition of amenability is that we have these Foner sequences, which basically means, what this means is how much AN changes when we let another element act on it. And this is kind of the boundary of AN. And this just says that the boundary of AN relative to the actual size of AN goes to 0. Z satisfies these by just taking intervals, minus NN. We can talk about that more later if you want. To get a left invariant finally additive probability measure from this, we take an ultra limit of these things. I can't say much more. There isn't. I think the best intuition is that these exist, and if these exist, then you have a Lifapum. As I said, it's not constructive, so I can't really draw a picture of it or anything. Maybe I can. Maybe someone out there knows a better way to think about it, but I don't. This is the annoying thing. It's that it's not constructive. And likewise, I have loads of groups with a Lifapum. Getting the Foner sequences isn't really that easy. Yeah, we can continue discussing things after if you want. So.